Hello everyone, thank you for joining this presentation today. My name is Nima Hosseinzadeh, a PhD candidate from Civil Architectural and Environmental Engineering Department here at University of Miami. I'm working with my advisor, Dr. Pranoy Soraneni. And today I'm honored to present one of the chapters of my thesis as my PhD, which is on synergistic effects of air content and supplementary cementitious materials in reducing the damage in concrete exposed to high concentrations of de-icing salt and various temperature conditions. So we are going to start with the motivation that actually triggered us to start working on this project. Then we are going to be moving to our objectives, the methodology. We're going to get to some results while the research is still ongoing. We're going to get some interim conclusions, and then we are going to mention what are the next steps regarding to this project. So concrete pavements are a major component of our transportation infrastructure, which are usually designed and are expected to have a long-term performance. It's usually like 50 years or so, but in cold regions of, for example, United States, cities like New York or Chicago, early age damage of concrete pavements have often been reported. This usually happens like within the first 10 years or 15 years of the lifespan of the structure. However, they are designed to last for like a longer period of time, like 50 years or so. So what is causing this damage in our concrete pavements? So first, they are attributing this damage to the freeze-thaw cycle. So as most of us usually know this, we have temperature variations daily. So the way it works, usually over the nighttime, the temperature drops and it drops below the freezing temperature of water, and over the daytime, the temperature increases. So this is going to happen over the time, and we have water in our concrete. And what happens when the water in the concrete freezes? It expands, and this expansion is going to cause internal pressure from the inside of our concrete matrix, which can lead into cracks and deterioration of our concrete structure. In addition to that, we use de-icing salts, which can form calcium oxychloride while they are in interaction with calcium hydroxide, which is in the hydrated concrete. So calcium oxychloride is an expansive chemical, which is also going to lead into internal pressure, which also can lead to the cracks and deterioration of our concrete pavement. But are there any solutions to prevent this damage? Yes, there are. So first, we can have entrained air in our concrete. We use air entraining agents and admixtures to induce these entrained air in our concrete. The way this works, this air is going to provide some voids and stress relief spaces in case those expansions happen. In addition to that, we can replace a portion of our Portland cement in the mix with supplementary cementitious materials like fly ash or slag. How is this going to help? So the theory is that by replacing a portion of the Portland cement, we are going to reduce the amount of calcium hydroxide formation, which is also going to result to less calcium oxychloride formation. This is going to help to prevent the formation of that expansive byproduct. So AASHTO PP84 suggests that you can replace 35% of your Portland cement with SCMs to reduce this type of phenomenon. In addition to that, you can control your calcium oxychloride into less than 15 grams per 100 grams of your cement paste. But what is the missing pieces in this criteria that we had? So first of all, the AASHTO PP84 oxychloride specifications are mostly based on the work done on cement pastes. In addition to that, the combined effects of different SCM types and entrained air in reducing this type of damage is still unknown. So that's why our objective in designing this experiment was to provide a relationship between the air content, the SCM type, the SCM content, and expected lifespan of concrete exposed to de-icing salts, which is calcium chloride in our case, and freeze-thaw cycles. So let's talk about our methodology and the materials that we used. So in this table, you see that we use type 1-2 Portland cement, we use class F fly ash, and blast furnace slag. The coarse aggregate were oolitic limestone with the nominal maximum size of 25.4 millimeters, and the absorption capacity was measured to be 3.75%. And the fine aggregate was silica sand with nominal maximum size of 4.75 millimeters with absorption capacity of 2.84%. And as our de-icing salt, we use commercial de-icing calcium chloride with purity more than 95%. In order to have the visual damage which was expected to happen in our concrete cylinders being classified and tracked over time, we created this visual damage classification, starting with none, when no signs of cracks on the ends and sides of our concrete cylinders were seen. Then, of course, we had minor, when short and thin cracks on the ends and in some cases around the edges of our concrete cylinder was observed. Then we have the moderate classification, which is when long and deep cracks on the ends and some cracking on the sides of the cylinders were observed. Then we have the severe, which is when large amounts of spalling at the ends of our cylinder and some crackings on the side and the middle section of our concrete cylinder is observed. And then, of course, we have the failure, which is when more than half of the cylinder has spaled and long and deep cracks throughout the volume, and the UPV values, which are going to be measured, were around 0. So, as we mentioned, the objective was to investigate the damage in concrete with different air contents and SCM replacements when they are exposed to freeze-thaw cycles and they are submerged into concentrated calcium chloride solution. In order to get to that, we had our concrete cylinders casted with the dimensions of 4x8, and they were cured in the moisture for 28 days. The exposure was a freeze-thaw cycle. Each cycle took 48 hours. In the first 24 hours, the samples were submerged into 25% of calcium chloride solution inside a freezer, which the temperature was measured to be around minus 10 degrees Celsius. In the next 24 hours, the samples were taken out of the freezer, submerged into the salt solution, and they were kept in the ambient condition, which was measured to be 23 degrees Celsius. And the tests that we utilized for keeping the track of these measurements and the damage that was going to happen in them was compressive strength, UPV, bulk resistivity, surface resistivity, visual monitoring system that we talked about in the previous slide, mass change, and thermogravimetric analysis. As of today that I'm presenting this to you guys, we've experienced 260 freeze-thaw cycles, which is equal to 520 days of experience. And here I'm going to get to the results so we can spend more time on discussing the results, starting with the compressive strength values versus the air content, which was measured before samples were exposed into these cycles. So as the air content increases from left to right, you see that compressive strength decreases, and strength draw varies based on the SCM type. And with the fly ash, as you can see over here, you are experiencing the highest drop. On the right side, I'm showing to you the bulk resistivity values versus air content. The same from left to right, the air content is increasing, and with this increase, the bulk resistivity is generally increasing, and the SCM type and the content has a somewhat complicated effect on the bulk resistivity values. In this slide, on the left side, you see the surface resistivity values, which were measured for a large amount of samples versus the bulk resistivity, and it's obvious that you're experiencing a strong linear relationship between these two values, and that's why the surface resistivity was not measured in continuous of this study. On the right side, you can see the bulk resistivity values for our control mixes, which were just having OPC with various amounts of air as the cycles initiated. So you see that as the samples were submerged into the de-icing salt and the cycle started, the bulk resistivity has decreased, and this keeps happening as the exposure duration increases. The same case for the samples containing fly ash with different amounts of air, the trend holds for all of the mixes, whether they have the SCM in them or not. And it's the same case with the samples containing slag in them. And as noted, the initial resistivity was affected both by the air content as well as the SCM type and their portion in the mix design. All right, in here you see the mass changes which kept measuring them as the cycles were happening versus the cycles on the horizontal axis. This is the figure for our control mixes having different amounts of air. So as the air content increases, the mass change is reduced. It's the same case for the samples containing SCM. Here we have the fly ash. So the mixtures with higher SCMs are experiencing less change in mass. And it's the same case for slag. We have the air content increasing, and it gets just more complicated when we have both air and the SCMs presented in our mix design. And as you can see over here, we have our visual assessment classification. So the ones having the red color at the tip of the bars, it means that they have already failed. The one with the green color have not experienced any sign of damage. So the mixtures with no entrained air are failing at a very early ages. As you can see, the ones with no air over here, no entrained air, sorry, this here, this one here, and this one here, they have already failed at very early stages. And it appears that 28 days of curing is insufficient for the ones having fly ash in them. And both air and SCMs are significantly increasing the time to failure, as we can see here from left to right. And SCM type and replacement levels are affecting the time to failure significantly. Here I put some pictures that we had as we are measuring our cycles. You see how the samples are failing for samples containing fly ash versus samples having no SCM. And at the bottom right, you see the calcium oxychloride crystals that have formed on the surface of our concrete cylinders. So let's get to some interim conclusions based on the results that we have so far as we're still continuing this experiment. So the damage evolution is generally slow, and some mixtures show little to no damage after being exposed to several months of testing. The damage is reduced due to increasing air content as well as SCM replacement. There is an interplay for sure between air content and SCM replacement, and that's why for the best performance is seen in the mixtures with high air contents and SCM replacement levels. And in addition to that, visual analysis, bulk resistivity, and surface resistivity are all good indicators of damage progression, although bulk resistivity measurements can be tricky due to how is the dry condition of our samples. And finally, only specifying SCM replacement for durable concrete mixtures is likely to not be enough. And it's really critical to specify the SCM replacement levels as a function of air content to have a better solution. And through this relationship, we are going to have a more durable concrete mix in such severe conditions. So what are the next steps? So first of all, this is an ongoing research, and we need to finish the data collection for this phase, which are still ongoing for 6 mix designs, and we need to stop the cycles. And since this research was a part of my thesis, which is made out of 3 other phases, this preliminary data is going to help us to decide where to stop and how to treat the remaining phases. And with completion of this study, both the overall and specific objectives of the study will be achieved. And overall, this work will lead to significant savings in cost, which is mostly in repairs, time and labor, and of course, use of natural resources. Thank you so much, and I will be happy to take any questions that you might have in the chat or the Q&A.
Great, thank you very much.
My pleasure, thank you.